So I'm working with user land. That should change at some point to the user SuperFRS. But I have a directory. In this directory, this is called like that. Land user land SuperFRS. And in here you see all the foci.
Yes.
Yeah, that is according to our map. So, and now I have connected the first computer to this. So it's computer 235, and it is connected to FPF2-2. So it's the second detector of FPF2.
All right.
And if you want to know how it is, I made here also a text file, and you can do a more notes. And then you see which computer name
Correspond to which station?
To which station.
Yeah.
So, and by chance it was not the first but the second computer. So this is the pre-separator. So that is the P, focus P. Yeah. And I have connected this computer to the current SuperFRS detector. So we are working at the moment with the pre-separator 2. So, and in here there is the duck window, so we can start the duck. It's actually done automatically for all 14 nodes. But in here you will also find a set all. And if you look what is going on in here, that is what you have to do also for slow control. So, well, this is just a checking. So if everything goes well, we should see on SFP0, 6 ports. On SFP1, 2 ports. On SFP2, 6 ports. And on SFP3, 2 ports. So that would be down, right, left, up and left. But this is also, one can arrange where we put, we have 4 readouts, 4 SFPs, and they are connected like that. So then every board needs to flip the input signal. You can choose positive or negative input signals. And in our case, we have to write in this register a 1. Yeah? And you have to do that for all boards. So 0, from 0 to 5, 1, 2 boards, 2, 6 boards, and 3, 2 boards. And then we have to set the thresholds. So for the thresholds I have 2 methods. We have either individual thresholds, so every channel gets 1 value, or we have a common threshold. At the moment I'm working with a common threshold, and you see that here we are writing the same threshold value to all boards. Yeah, but later on
we need to specify.
We will write 128 thresholds per board for each channel. And then the bias, so you know that these IPMs have a bias from 52 to 55 volt or something like that. And we write it in hex numbers. So every board in this address we write the bias. So the first number here is always 1, and then this second number here is hex number of the bias divided by 400. So if I want to have 53 volt, I have to multiply, I think, with 400 and then write it in a hex number in here. Yeah, and that's it. So we need invert the signal, write a threshold, and set the bias. And these are the slow controls. And then just for checking, I'm reading out the scalar values of the FPGA. So
that's similar to the prototype.
That's similar to the prototype.
Yeah. So.
And I think even the addresses, the registers addresses are the same.
All right.
So, and then at the moment I have switched it off, so we cannot do anything. But at the beginning you will read as a scalar value 0, and then it takes a while until the voltage is on, because the voltage is ramped very slow. Yeah, so you have to wait a minute. We don't want overshooting of the voltage, because then this IPM is dead. Yeah, so we go from lower values to higher values rather slow, and go to the value from the bottom, never overshooting. That's why it is
So
a bit
you
slow.
need ramping up
We need
and
ramping
ramping
up.
down.
Yes, we
Okay.
need ramping up, that's for sure, and we don't want to overshoot.
All right.
And so it takes a while after you set the voltage. It takes a while until you see the result.
Okay.
Yeah. So, and that's
you,
it.
You need the ramping time. How many seconds?
I think it's a minute or so until
A minute.
it has
Okay.
until it has the bias.
All right. Okay.
Yeah. And then it stays always at this value.
Okay.
If it cannot reach the value, then probably you have a light leak, so that you have too much current, and then you cannot sustain the voltage.
All right. So things is clear.
Clear?
Yeah.
Good. Yes.
Yeah. But I will start first with analysis. After I finish this task, I will move forward for the slow control. Would that be okay for you?
Yeah, of course.
Okay.
That is up to you. I mean, whatever you prefer,
Okay.
no problem with that.
And yeah, basically, to develop the Apex application, I will need a detector to be on.
Yes.
So
I will check now the temperature, but my plan was
Not
to
now,
leave it running all the
not
time,
just- yeah.
because we also need to get a feeling
yeah.
how robust it is.
Mm.
You know, if the duck crashes every day, then this is also valuable information. This we don't want. So my plan is to leave it running for a longer time.
Okay.
And then you can always connect to the stream. You don't need an LMD file.
Yes.
You can read from the stream.
The same stream that you provided.
Live data, yeah, the stream is always the
Always is
name
not, okay.
of the computer. So you have the stream 86L-235.
All right. Okay. So.
Okay, and you know, we have discussed, so you know there is a find time and a cost time
Yeah.
for each channel, and we construct a time out of that. But for the test experiment at Heidelberg, we also had this detector in the beam.
The old one or the new one?
This one,
The new one.
the new one.
Okay, so the one that
The new one is in
Irakli doing
Heidelberg.
is the one, the new one, or Irakli has different.
Irakli?
Yeah.
No, he got from me one of the older ones
Older one.
for his tests.
All right. So then.
But in Heidelberg we had this one.
So Heidelberg is alone, fiber alone, or fiber with some detectors?
No, fiber with some detectors from R3B.
R3B, okay, so-
Pass module and so on and so on. But but the point I want to make is that I tested a method, a very fast method, to make an online display. Yeah, and so in principle you don't need the times at all. The very basic way of reconstructing an event is the channel number. So in your data word, you have a channel number, you have a find time and a cost time.
Yes.
And I was just taking the channel number. I was not doing any find time calibration. Yeah.
Okay.
I was just taking the channel number, and then I looked for channel numbers which I saw up and down.
Yes.
Yeah.
Yeah.
And these I plotted.
Okay.
And then you get a wonderful beam profile
Wow.
without
Timing, without
timing.
just
Yes,
as a hit,
so
fiber hit.
you see, in real life, when you are not sure, do I have a find time calibration or not, or where is it written or whatever, yeah, and also this is by far the fastest way So if you want to, let's say you turn the magnet and you want to see an online result, this might be a good method.
Reasonable, yes.
Yeah, because when I read the times, then I have to do the fine time calibration, then I have to go through my fitting routine. Of course, the position will be more accurate later, yeah, and the plot will look nicer, but this all takes time, and that will lead to a delay. Yeah, and then you turn the magnet, and then you have to wait until your online display shows something. Yeah, and that might be not so convenient.
Right now,
So for the analysis of data, of course, one can do the full
analysis.
Analysis, because we can make a cut on the times, we can make cuts on time over threshold, and we do the fitting of the position, all the full story. But for online, this might be much simpler. Just to look for channel, and then of course you have noisy channels up and noisy channels down, but the coincidence is very powerful.
Right now I have, I think, better than 100 kilo event per second.
Yes, because
at this moment.
Because right now you have to see that I want to see muons. This detector is not built to see muons. It is for heavy ions. Heavy ions make a lot of light. Many photons, and I can set my threshold very high, and then the detector will not say anything, until an ion comes and makes a lot of light.
Yes.
Now I want to see muons.
All right.
And to see muons, I have to set a very small threshold, close to the baseline.
Yes.
And you see that every CPM fires with roughly 1000 hertz, 1 kilohertz, every CPM. Yeah. So they are constantly firing, but my trigger is on the cosmics. Yeah. And then if you look at coincidences, even if the up CPM fires with 1 kilohertz and the low CPM fires with 1 kilohertz, within your time where you read out, the chances that both fire at the same time is very little.
Yes.
If it's rate 1 times rate 2 times the time where you look for a coincidence.
Yes.
Yeah? And that, so coincidences is a very powerful tool.
Yeah, indeed.
Yeah.
Okay, so things.
So, and this we can test, and if it now works with the cosmics, it will for sure work with
For
iron.
ions,
Yeah. Because then, as I said, the threshold is higher, the rate of each CPM is much smaller, basically zero. If I want to detect uranium beam, gold beam, silver beam, argon beam, I can set my threshold so high that the CPM will never fire with thermal noise or with anything else.
All right,
so this is the most difficult situation we have now with the cosmics. If we get it working with cosmics,
then it will work
always
with anything else.
Yes. Yeah. Okay.
Okay, so now let's go back to the